Good morning. This is the talk that I gave to the Scuola Superiore Sant'Anna. We were unable to register for some reason, probably it was my fault, but I'm going to repeat more or less the talk on the same line. We're going to have a look on what it means enhancing human-machine symbiosis via exosuit. I lead a laboratory that is called ARIS Lab, that stands for Assistive Robotics and Interactive Exosuit Laboratories. We have quite nice facilities in Heidelberg with several people, very diverse environment. And our philosophy is mainly to design everything in-house, from sensing, actuation, control system design, and also all the part related to the components that are built in together to make an exosuit. I will start from this slide that represents the first example of an exoskeleton from Ralph Mosher in 1967 that was defined by him as a symbiotic unit with the alacrity of man's information and control system coupled with the machine's power and ruggedness. It was the very first example of exoskeleton. Unfortunately, for that time, it never worked, but it was extremely inspirational for all the generation of people that wanted to challenge themselves in this kind of field. Over the course of the year, there has been a paradigm shift. We started from very rigid exoskeleton for progressing towards softwareable exoskeleton or exosuits. Despite these two technologies seems to be one the evolution of the others, I am not at all convinced that this is a progression towards total improvement. However, these two systems are complementary, because it's true that an exoskeleton probably has a limited bandwidth, high rigid components, and a heavy weight. However, it is much more able to deliver high torques, while an exosuit is something that is thought to have a higher bandwidth, deliver lower torque, and being a bit more portable. So these are two complementary technology. One does not exclude the others. For what concerns exosuit, we are going to go through how to design an exosuit, and above all, I would say the main core of the presentation will be the part related to the control system design. Exosuit, as you know, is something that started more or less around 2010, 2011, 13. I remember the first paper was from Harvard Biodesign Lab, from the group of Connor Walsh, and was something related to mobilization of lower limb. Lower limb, there are several other examples with different kind of actuations, but there's also a part related to the exosuit for upper limb. And this is another, let's say, branch of exosuit, upper limb and lower limb. They are very distinct for what concerns, for example, the part of the control implementation. How does it work, a softwareable exosuit? Is something that consider actuation that are embedded into textile frames or harness, and this harness provides torque at the level of the joints by closing the loop using force sensing and understanding what is the phase gate. So depending on the phase gate, you will have an assistive profile that will be delivered and closed by force sensors inside the control loop. The system works pretty well. You are able to decrease the oxygen metabolic consumption of a significant amount, not only during running, but also during walking. There are other branches of softwareable exosuit, for upper limb, for example, that counts or relies on a different kind of actuation, inflatable actuation technology. This is something still from Harvard Biodesign Lab. You have a polymeric system that when is inflated, assume a different, or is pre-shaped in such a way to deform according to a different pattern and allow the closing of the hand. So what do we do in the assistive robotics and interactive exosuit? We design our own technology, and we comprise different examples for what concerns both upper limb and lower limb. Hip, elbow, and hand. We are also working on the shoulder, but I'm not going to show anything because it's still a very preliminary stage. If we want to design an exosuit, we have to consider different kind of, let's say, expertise, starting from ergonomics in order to design the harness that comprise all the sensing and actuation of the exosuit, to the actuation itself, the choice if you want different kind of electromechanical or inflatable systems, and then the control, how to master the nonlinear behaviors inside a soft wearable device. What about actuation? Let's start from this pillar of designing an exosuit. Well, actuation is always inspired in order to match the human musculoskeletal system that is still unmatched in terms of power-weight ratio. But there are also electromechanical actuation for tendon-driven unit, pneumatic artificial muscle, twisted springs, shape memory alloys, and pneumatic interference actuators. In this presentation, we will deal with this kind of system. The first example of actuation that we tried to test it was a clutchable actuation technology. This clutchable actuation technology consisted in all the package of the actuators that has been relocated, like you do in the usual exosuit. This is the advantage, far from the joints that you want to mobilize. And electromechanical clutches that engage the connection with the actuations once the assistance is requested by the person. So here you can see a system with a clutch that is not yet engaged, but when, for example, we trigger the assistance by a button, by a simple button, the clutch connected less than 50 milliseconds. Why is something interesting? Well, because using electromechanical clutch, you can employ just one actuator that is continuously spinning, and then using set of clutches you can engage or disengage different joints that you want to mobilize, yet using one electromechanical actuator. This kind of approach is called one-to-many. I'll show you how it works. So the idea is having one single system with an electromechanical actuator rotating, continuously spinning at a very high speed. Here it is. And then two different sets of clutches that, once are they engaged, they deliver torque on the left arm or the right arm. In different directions, because you have counterclockwise and clockwise gears, so you are able to follow engaging or disengaging the different clutches, different trajectories. This is an example. The actuators is always spinning in one direction, but switching the two clutches very fast, you are able to follow a sinusoidal, of course with a certain level of approximation, a sinusoidal trajectory. You can do these things also when you set up the system on a human subject. So here we see an example. Here there's the actuators behind the person. You pull up the arm and then you lock it in position. In the meantime, the other clutches are connected and disconnected on the counterclockwise and the clockwise wheel in such a way to have different trajectories or flexion or extension. Of course, the limitation is that since the single motor behind the person is rotating at one single speed, the maximum speed that you can reach is always the same, so it's always constant. Another example is routing tendons around the articulation. Here you see the electromechanical actuators. Inside the gloves there's a very simple flex sensors that detects the motion of the hands and amplify the velocity by a negative damping. Extremely simple. There's an intrinsic damping inside the system itself, so the system, the control will never be unstable. An example we use also, I would say, for this kind of approach, machine learning. This is a very simple example. It's a recent paper. We detect the signal from the forearm of the person. We classify this kind of posture using a machine learning algorithm, and then we drive two electromechanical actuators in order to move the thumb or the other fingers and pre-shape the hand, and online regulating also the assistance based on the activation of the muscle in the forearms. You can use also additive manufacturing in order to tailor the system in a better way on the anthropometrics of the person. So instead of using textile that sometimes to be assembled requires a lot of skills, know-how, as well as time, you can measure some part of the hands, put inside the parametric software that we implemented, and then the 3D printing system will print out the palms, the fingers, you have to sew a bit and just prepare the system in a more ergonomic way, comfortable way. So this is your palm, then you assemble the fingers, you put inside the cables, and you have, so here you attach two clutches by a magnetic coupling, and then you have assistance from the system. We designed something in a better way here, so all the actuation and control is inside this small box that is wrapped on the forearm, and then you have a completely 3D printed system that is able to mobilize for both flexion and extension of the arm or the end. How does it work? Well, this has been thought to be sort of product for startup, so there's no complex control inside. The control on which it relies is vocal control or a button, or if you shake your arm, the system will open. If you shake again, the system will close. This is how we use it with the Spinal Cord Injury Center of Heidelberg University. The person is affected by spinal cord injury, of course, has problems for what concerns the manipulation of objects, simple object, doesn't have enough force. But as soon as you provide this kind of technology, once you activate, the system is able to allow the person at least to have compensatory strategy to hold an object. This is another example, still in collaboration with the Spinal Cord Injury Center of Heidelberg University. Now, let's talk about control. That is the main core of this presentation, because controlling exosuit is different from controlling a rigid exoskeleton. I would say that rigid exoskeleton mostly relies on a classic control for industrial robotics. Here we have a bit more, let's say, nonlinear behaviors to master in order to be able to control the system in a robust and stable way. I will make a differentiation between upper limb and lower limb, yet in these controllers what you have to understand is the reference can be a force or a position or a velocity. Here in this case it's represented by a force that you have to send inside the control scheme in order to make the control scheme working and delivering assistance in a proper way. You imagine this kind of control, since it's a wearable system, is in parallel to the human biomechanics. We need to extract information of motion and then deliver inside the control system. Let's talk about upper limb. Usually upper limb is driven by what is called, at least for our experience, admittance control. An admittance control strategy allows to detect the force at the interaction with the exosuit and transform this force into a velocity. And this velocity should be communicated to the electromechanical actuation. This is admittance control. So the first controller that we designed was a pure force control that was incorporating a biomechanical model of the arm, a three-dimensional model of the human arm, like a double inverted pendulum. There are two different loops inside. We detect the motion of the person via two inertial measurement units, and then we send this position or three-dimensional configuration of the arm of the person inside the controller that decides what is the compensation of gravity. And then we close the loop with the force sensors in this way. This is the force sensors with the tendons that detect the motion of the person. Two inertial measurement units connected via Bluetooth low energy communicate with the controller that is posed on the back and where the actuation is located also. And then we compensate for gravity by closing the loop around 250 Hz on the force. You see that the cable never slack. Now, how do you test if the system is effective or not? Well, you have to test the system by a sort of graphical user interface, asking person to follow a trajectory that is proposed on a visual feedback on a screen, and then comparing the reference trajectory with the actual trajectory that the person is performing with and without the exosuit. So the idea is that if you make a motion of flexion and extension of the L at different velocity, you will see that you will find a delay in motion and the decrease of the accuracy when you go faster. This is of course due to the fact that the exosuit is not able to follow trajectories that are fast. There's a delay. You need to understand what is the force, so the movement initiated, you have a mechanical or a flexible structure that has its own intrinsic proper delay, and this delay is then reflected in the ignition of the assistance from the controller. This is true for what concerns the kinematics. You see, for example, the dotted trajectory is the one that the person should follow. This gray line is how is followed the trajectory on the screen without the exosuit, and with the exosuit is this thick black line. So when I go at a certain velocity, I have already a delay in initiating the trajectory, but if I go faster, of course, the exosuit follows less. Even if I am able to attempt without the exosuit, I'm able to follow the trajectory in a much better way. This is true also for what concerns the amount of torque, is the green torque, the biological torque, that you have to input inside the system to follow the trajectory. So you have also almost to backdrive the system for very high speed. This is reflected, of course, for what concerns the torque that you have to apply by your contraction of muscle to the elbow, and of course the change in biological torque that you see for low speed to high speed. Now, how can you design something that is more symbiotic? How can you increase the responsiveness and the promptness in response from the exosuit? You have to include biosignal in the loop. You have to detect when the person attempts to move before the mechanical motion starts, the real one, and then input inside the control and try to have the controller that is fast enough to start the electromechanical actuation in such a way that the motion between the exosuit and the one with of the human are in parallel or synchronous. The idea came when I spent part of my time at University of Twente with Massimo Sartori. Massimo Sartori is a person working in biological modeling or biomechanical modeling, and we designed for the first time what is called a myoprocessing technique. A myoprocessing technique is detection of electromyography, joint angle by the inertial measurement units, and input inside a block that is able to detect the motion and transform this motion into muscular activation, velocity of contraction of the muscle, so what is called muscle tendon kinematics here, and then transforming, understanding what is the force at the level of the single muscle and scaling up these muscles inside the anthropometric of the person that is wearing the exosuit. So if we go a bit more in detail, we have electromyography that goes inside some function that detects, depending on the amplitude of the electromyography, how many muscle fibers are contracting. Then you have the joint angle that are communicated by the inertial measurement units that detects the motion of the arm, and goes inside the muscle tendon unit kinematics that tells you what is the velocity of contraction. It goes inside the muscle tendon unit dynamics that tells you how much is the force, depending also on the pernician angle of your biceps, and then everything is scaled down inside the biomechanical model of the person that is wearing the exosuit. The first attempt worked decently well. So here you see the signal from the different muscles that we were understanding by extracting EMG with different electrodes. At the time we had about 4 or 5 electrodes. And this is the generation of online torque that needs to descend inside the electromechanical actuation. Okay, it seems to be more prompt, you can move faster. An example of implementation is this one. With and without the exosuit, here we were estimating the goodness of the trajectory, and if the usage of the exosuit was changing the physiological motion of the person. You see that in these two plots how the electromyographic signal from the biceps is reduced when you use this kind of technology. In terms of tracking accuracy, you don't find anymore for different velocity this gap between the initiation of motion with and without the exosuit with respect to the reference trajectory. This is much less pronounced rather than in the force control. So this means that the system is able to have, the overall control system is able to have a higher bandwidth of response and match more, let's say, but not completely, the bandwidth of motion of the wearer that is using the exosuit. Something that was interesting is that if we pass from no weight on the hand to 1 kilograms and 2 kilograms, and we look to this upper row that refers to the electromyography that we have acquired for the biceps, that is the one lifting the object, the muscle that is mostly involved. This gray line represents the increase of the electromyographic signal in the biceps when I'm not using the exosuit. Of course, it increases from no load, 1 kilo to kilo. When you activate the exosuit, what you have is that independently on the amount of weight that you're holding on your hand, the signal from the electromyography remains roughly the same. There's no significant change. What does it mean? Well, it means that without tuning any gain, the myoprocessing technique allows to initially estimate what is the amount of activation of the muscles and then tuning up or down automatically the amount of assistance that is provided by the electromechanical actuation. Under this point of view, I would say that the myoelectric or myoprocessing control is superior to the force control. But of course, we want to test who's best between the two. Because it's true that force control doesn't have adaptive, automatic tuning depending on the external load, but it's also true that the implementation and the calibration of the pure force control is much easier rather than having a myoprocessing force control, a myoprocessing control. So what we have done is just we implemented inside the same exosuit the possibility of switching, because they cannot work in parallel, but we can switch automatically between myoprocessing technique and pure force control. In the myoprocessing technique that we refer to dynamic arm in our works, remember that we don't have biosignal in the loop, we only have detection of force and then transformation of this detection of force inside the velocity. In the myoprocessing control, remember you have detection of myoelectric signal, detection of motion, and then transformation inside the velocity, but there is biosignal in the loop. Now, we tested the system on people, on subjects, and we didn't tell them what kind of controller were they using. Okay, it was, let's say, pseudo-random, the utilization of the controller. We went from very accurate motion, pick and place, different objects from one position to another one, to very dynamic tasks, like launching a medical ball of about 2 kilograms, or having a person that was blindfolded and perturbing the arm in such a way to understand if the controller was able to stabilize and it was robust. And then we compare the two controllers. So if we consider, for example, this testing here, that is the step response. Person is blindfolded, and this is how the two systems are responding. Let me stop him here, otherwise it's too noisy. So what we can see here, well, we tested the system in such a way, for example, to have to understand which between the two systems is faster in moving and which between the two controller is faster in stabilizing. So what we can see here is that, for example, for what concerns the myoprocessing technique and the comparison with the force controller, the response time of the myoprocessing controller is shorter rather than the one that relies on pure force detection. Okay? Significance difference. This has been tested on more than 10 people, and this is what you see is the average also for what concerns the curves. Still, The comparison between the two, despite the highly significant difference, we are talking about 350 milliseconds and almost 400 milliseconds. However, the microprocessing technique is the one that wins, is prompter. That is something quite intuitive, because when you let the ball falling down, there's a contraction of the muscles, and then there's the transmission of the force to the force sensors. So first there's contraction of the muscle, generation of a myoelectricity signal or myoelectric signal. So the one that relies on biosignal in the loop is fast. When you consider instead the settling time, so the time that the controller needs to stabilize after the sudden impulse, we have that the force control relies much better, significantly better. Motivation, it might be, this is something that we didn't understand, but we can speculate that this motivation is due to the fact that the electromyographic signal is a noisy signal and is input inside the controller. So probably the force controller relies only on detection of force and stabilization without insertion or intake of also a myoelectric signal inside the controller itself. And EMG is noisy for nature. In terms of time response, I would say without the perturbation, but which is the two when I attempt to move that is faster in reacting? The myoelectric control or the force control? Well, of course, the myoelectric control succeed in sending out a calculation of the torque in more or less 70, I would say 65 milliseconds. That is comparable with the electromechanical delay. That is a physiological time between the opening of the ion channel and generating of the motion, is our internal bandwidth at the level of muscular contraction. And then the force control goes 150 milliseconds. So this means that there's a significance. However, 150 milliseconds against 70 milliseconds is quite a, let's say, a fast response for both the controllers. What about the pick and place? Well, the pick and place, here what we see is that depending on 200 grams, 500 grams, and 1 kilogram, the capacity of the myoelectric controller of increasing the assistance, because this is the torque that is calculated, still is compared to the force controller with a rising trend. So it means that when I grab something that is heavier, the system understands and ramp up the assistance. But this is only for the myoelectric control, because the force control remains flat in terms of torque or calculation of torque, independently on the object that I am grabbing or I am picking and placing it. What kind of bandwidth you can reach with these two controllers? They are quite fast. You can move more or less, I would say, at the human speed. With 2 arms, consider that this ball is 1.5 kilo and that one is 2 point something plus. So overall, I would say that the microprocessing technique is the one that assures, I would say, higher bandwidth of motion, promptness, understanding of the biological torque that needs to be transmitted. However, it implies long and extensive calibration, because you have to go in the motion capture lab, performing some muscular contraction, motion, and then setting up all this information inside the controller. The pure force control, basically you put 2 values, that is the weight and the height, and eventually some very, let's say, not highly approximated anthropometric measure, and the system will work. Which I prefer between the two? This one, okay? This is how it works, also, during Corona time. Now, what are the clinical application of this kind of system? Well, you can use we use the force controller. The force controller has been used for the first time in spinal cord injury. You will see here, for example, a person that is has a damage in the cervical 5 vertebrae. Is not able to move. The system is now switched off. But when you switch it on, the residual capacity of motion is automatically amplified, and that small amount of motion that the person can still perform is then transformed into a trajectory via using the amplification from the initial measurement units and compensation of gravity. We tested the system also on multiple sclerosis. Multiple sclerosis, the damage, it depends on the level of the illness and the severity of the illness, but sometimes people affected by multiple sclerosis has problem in motion and endurance. So what we have done is we used the same controller, and you can see that, for example, no exo and with exo, we have increase of the range of motion of the elbow. The velocity, because sometimes you have spike of velocities on average much smoother with the exosuit. And same for what concern, this is more important, the biceps activity. The biceps activity, of course, is smaller because you have support from the exoskeleton or the exosuit. To estimate this, we use high density EMG. We found that the normalized volume of the high density EMG, here is with the exo and here is without the exo. Imagine is the high density is a band that is wrapped around your arm. So there's a statistical significance between exo and no exo. And then of course you have statistical significance also for what concern the conduction velocity and the endurance time of the person. So the person is able to endure more performing some kind of exercise that we're holding objects or moving objects from one place to another one. That is the typical, let's say, rehabilitation practice that is done for this kind of illness. We have also an application with functional electric stimulation. Functional electric stimulation merged with exosuit. What's the reason behind? The reason behind is that when you use functional electric stimulation, you innervate muscles with via injecting current, and usually this kind of technique is favorable for what concerns prevention of muscular atrophy, because you are injecting current in the muscle and you make the muscle works, so you stimulate the muscles. There's also a part related to recovery and plasticity, because part of the current goes into the peripheral nervous system in the neuromotor neuron, but we are not going to consider this kind of aspect. What we consider is that when you inject current into muscle fibers, recruitment usually is much more selective for what concerns large muscle fibers. With large muscle fibers, your motion is very abrupt and jerky. And also there's another problem. Recruit large muscle fibers involve much more consumption of oxygen and then onset of muscular fatigue. So you start trembling very early, you don't have a lot of endurance. So what we have done is just in collaboration with Kraut Timmerman, that is a producer of functional electric stimulator, we connected the system via Bluetooth Low Energy. So you attach the system to the biceps, and then the system communicates with the controller that is in the exosuit. How does it work, functional electric stimulation integrated with electromechanical actuation, EMG? The system, the stimulator, has a dual functioning. It's able to measure the EMG, then closing the channel and sending the FES. What we do, we measure the minimal amount of EMG. This is, of course, a healthy person. It's one of the students from Polytechnique of Milan that was visiting us. The person attempts to move. There's a minimum amount of EMG that is sent to the controller, and this allows the controller to estimate how much electromechanical assistance and how much of the functional electrical assistance. So you have a double action, that is injection of current and gravity support from the exosuit. This is what happens to a person that is solely assisted by functional electric stimulation. You see this abrupt muscle contraction and motion, while a person with exosuit is able to have still muscles that is contracted. However, the electromechanical assistance allows, for example, here you see hybrid controller is functional electric stimulation plus FES. NMS is only FES, neuromuscular electric stimulation. So the fatigue level, the onset of fatigue, that of course can be calculated by the frequency of the electromyographic signal is much lower with the hybrid controller, as well as the number of repetition is significantly higher in terms of exercising using the hybrid controller rather than the neuromuscular electric stimulator. Another part of my research is in industrial or occupational exoskeleton. We have a collaboration also with Scuola Superiore Sant'Anna and some colleagues in Heidelberg University or in Germany. What we have done is just a keeping one of the industrial occupational exoskeleton produced by Hugo with a soft wearable layer that is worn beneath that works on compensation of gravity, like the one that I showed you in a bimanual configuration. So what it means that this is the first example of hard, soft, active, and passive occupational exoskeleton. The controller relies on a dynamic arm module, so on a pure force control, and here you see how it works. Okay, all the actuation vector is in here. It's about 1.8 or 2 kilograms overall. Now, how you understand if the system works well, physiologically speaking, or not? Well, there are several research that demonstrate that when you use this occupational exoskeleton, it's true that some joints are assisted, but the joints that are not assisted are contracting or co-contracting with levels that are much higher, rather than not using the occupational exoskeleton. So what we have done is that we perform some tasks, like the one that you've seen in the previous slides, and then we check what is called the co-contraction index that is calculated via this formula. And we demonstrated that over the course of the exercise, the co-contraction index between the shoulder and the elbow, where the two joints assisted, does not change. So it basically means that when you assist all the joints that are involved in a task, you don't have co-contraction index. That is different. How do you modulate the force or the assistance if you're not using a myoelectric signal in the loop? You can do it by using a vision algorithm. A camera that is here at the level of the chest of the person detects what kind of object you are going to grasp, and then recognizing the object, understand what is the gravity compensation that should provide when the arm grabs this object, because of course you have a different system once your arm grabs an object. This is how it works. So you have an algorithm here. Here you see the vision, and it tells you, oh, let me just start it. It tells you what kind of object detecting, depending on the object that you are grasping. The reference torque of the system change. For a heavier object, of course, compensation of gravity should be higher. So using an approach that is purely based on vision, we are able to remove the insertion of myoelectric signal in the loop and relying on vision to estimate what is the gravity compensation and automatically adapt. Now, let's go towards the last part of the presentation and all the part related to lower limb. The difference between controlling lower limb and upper limb is that in upper limb the manifold of motion of a human arm is quite infinite. It's large, it's very large, and detection of action is very difficult. For lower limb, you have to detect the different gait phase. Means that the person needs to walk, and then you detect what kind of phase he or she is, and then you automatically adapt the assistance. Now, what we have done is having our own system at the beginning. Is the first example of our softwareable exosuit. A single motor that relies on two inertial measurement units and two cables that actuates hip flexion at the level of the leg. We don't have force sensor in the loop. We do not detect the force, but we are able, by using the inertial measurement units, to understand what is the gait phase. This gait phase is then communicated inside the controller, and I will show you what kind of controller we are using. And the motor, the single motor, pull and release the legs in such a way to actuate Alternatively, the flexion of the hip and assisting the person. This is how it works, and the first paper that we published using nonlinear adaptive, or dynamic, adaptive oscillators, not linear, adaptive oscillators. So you detect the phase of walking automatically by using the inertial measurement units. Then if you increase the velocity, you need one step to recalibrate the oscillators on the phase and the frequency of the person that is walking. Yet you see that this cable never slack, is always kept in tension. Okay, so the assistance is smooth, the assistance is in phase with the person. Now, this is easy, putting the assistance in phase with the person when you are in a lab environment. Or when you are outside, this nice curve, that are the phase gate, is not something easy to detect or estimate via only using inertial measurement units. And in fact, you have this keep angular position that of course change depending if you are making a U-turn, if you change your speed, or you are following a path that, for example, is ascending. How do you do that? So how do you account for this sudden change? You have to use a sort of feature extraction algorithm, in this case is a machine learning layer, that is trained with data of person that are walking outside with solely the inertial measurement units. So we detect the gait pattern, we send and we train the algorithm, and then we let the system using still the same adaptive oscillators, but with the machine learning layer algorithm that is the one in charge for sending the signal to the output of the motors. And this is how it works. Okay, this is an example. So we are going down to the ramp, and you see that the cable are always in tension, and we are not on a treadmill. Does it work, this kind of approach? You have to test it. And you test it by using what? Well, you can use metabolic oxygen consumption. So here we are on a treadmill at 0.6 meters per second, 0.8, 1.1 meter per second. Without the exosuit, with the exosuit without machine learning, with the exosuit with machine learning. The difference in terms of metabolic consumption are present when you use the exosuit with and without machine learning, respect to the no use of exosuit. Yet there's no statistical significance between with and without machine learning layer. If you go outdoor, you find statistical significance also when using the machine learning layer. So this means that when you use this kind of recognition algorithm, the system is able to tailor the assistance automatically in such a way you have a delivery of the assistance that is much more in phase with the walking of the person that is wearing the exosuit. This was for a system with one single motor, but we have a version that is much more powerful, with two motors, that is able to independently mobilize left and right legs. How does it work? Well, we can use vision also in this kind of system. We have a vision camera that detects ascending stairs, level ground, descending stairs that we trained. And then this machine learning layer decides, once it detects the different states, level ground, ascending and descending stairs, how much is the profile that needs to be sent to the controller in order to actuate the legs. You send people, how do you train the algorithm? You send people without the exosuit with the camera around, and then you run classification algorithm, and you see that we almost have for level ground, descending stairs, and inclined stairs, we almost have here almost 100% of capacity of detection. Now, once you use it, check if I cannot increase the volume, but perhaps you will hear now when it's slightly higher. Okay, the amount of torque is higher. Without vision and without the exosuit, you will see that the physiological motion is not different, but you have a significance in the difference cost of transport, so how much oxygen you consume. Inclined stairs, level ground, declined stairs. You have statistical significance with and without vision, and between the exosuit and the no exosuit. This if you want to use vision, but if you don't want to use vision, because I understand that also the computational power that is requested for vision might be higher, so you need to add on top another module, you can use 3IMU, 1, 2, and the third here on the sham. You train the algorithm, sending people climbing stairs, descending stairs, and level ground walking, and then what you have is exactly the same results that you had before, but without vision. So you are able to detect this kind of pattern also without the use of vision algorithm, but just relying on machine learning using inertial measurement unit. You need to add just one more inertial measurement units. Does it work? Well, here we have capacity of detection of the different states, inclined, ascending or descending stairs, that is even higher. And also we have a decrease in the cost of transport that is highly significant when you use the exosuit with the machine learning layer algorithm, respect to when you do not use the machine learning layer algorithm, and respect, of course, to the unassisted condition. And if you don't want to use machine learning layer algorithm, we have our own, let's say, novel classic control. This novel classic control relies on a heat phase reconstruction, velocity and position. If it's something cyclic, it rotates. A Kalman filter, an extended Kalman filter, smooths all the part of detection, and then it communicates with the usual admittance control. Here you see, we can climb stairs, we can descend stairs. And the nice things of this kind of controller is that it's completely transversal and hardware free. This means that it can be implemented on the system with one single motor and the system with two motors. What's the results? We tested outdoor extensively in what is called the Philosopher Walk in Heidelberg. We have 1.2 kilometers of path, 216 stairs ascending and descending, and a path that is inclined, level ground, or descending. How does it work in terms of metabolic consumption? Well, here we have almost 22.6% for what concern the uphill walking, and overall 16% and 30% between the double actuation and actuated system, but without using any machine learning layer. And this is used extensively outdoor. Now, we are redefining the system because, of course, the design was a very rough design from the university, from a lab, I would say, but we collaborate with TU Dresden and their department of industrial design that are absolutely outstanding person, and we are redesigning our system in such a way to use the system also for what concern wellness. So I'm almost on the finish line. I would like to thank, of course, my team, that is the only one responsible for all the results that we have in our lab, and all the collaborators in Germany and around Europe that, of course, took part to all the research. I would like also to advertise that we will bring in Heidelberg BioRock 2024. That is the biggest conference in biorobotics, started also and initiated by and created by the Scuola Superiore Sant'Anna. And then with this, I would like to thank you for your attention and apologize for the fact that I was not able to activate my microphone when I gave the talk at Scuola Superiore Sant'Anna. Thank you very much.